Hello, today I'd like to talk to you about the ESHE chronology based on Bayesian analysis for the site of Chez Pinaud in Jonzac in southwest France. With the following question in mind: is the Quina Mousterian from this site really the oldest quina in southwest France? So this site of Jonzac is located in the southwest of France and was excavated by different teams between 1997 and 2008. It is a collapsed rock shelter sitting against a and here you can view on the bottom left hand corner a general view of the site as well as a map of all excavated areas. This site is quite famous for the bone bed located in stratigraphic unit 22, a bone that testifies of a Quina Mousterian industry associated with a huge number of faunal remains attesting to seasonal hunting of reindeer herds. Large number of reindeers were killed during successive winters. Here is a quick look at a number of lithics, and in particular at Quina. And when it comes to chronology, Richter et al. Published in 2013 a paper based on thermoluminescence of flints. And they published, what you can see in the bottom of this graph, what appears to be the oldest dated quina in southwest France to date. Now, if we look at individual ages, we can see that there is quite a bit of dispersion in the data. And actually, the average relative standard deviation of these ages is 12%. Now, if we then compare with the dispersion of gamma dose rates measured at the site, we get a relative standard deviation of 11%. So it is quite tempting in our view to explain the variability in thermoluminescence ages as the result of widely dispersed gamma dose rates. And indeed, if we look at the paper by Richter et al., we can see that gamma dose rates are quite variable even inside layers, and hence the dispersion of TLA. Now, why would ESL be better suited? Well, first because ESL is less dependent on gamma dose rate. Indeed, quartz grains receive mainly beta dose rates, of course also gamma, but to a lesser degree. The second point is that dosimeters in the case of ESL are placed at sample location, contrary to TL dating of flints, because the location of the dated flints is unknown before the excavation. And finally, ESL is generally more precise than TL, and that's purely because of luminescence protocols. But I won't go into details here. Now, to date Jonzac with ESL, we placed dosimeters at the sample location. We use high resolution gamma spectrometry to determine beta dose rates, and we performed single grain ESL measurements in the Bordeaux laboratory. Now first, let's look at the data. Here I plotted again in black the average TL ages as published by Richter et al. In gray the individual TL ages, and in red we have single grain ESL ages, so the new ages that we presented here. These single grain ESL ages were calculated using a model called the average dose model. And we can see here, first of all, that generally speaking, ages are increasing with depth. You can see here on the vertical axis, stratigraphic unit. The more towards the bottom we go, the deeper we are in the sequence. However, in stratigraphic unit 17, we seem to get something outlier. And if we actually calculate the average of the 6 bottommost samples, we get actually 2 outliers. One at plus 10% above the average in stratigraphic unit 17, and the other one at minus 9% below the average in stratigraphic unit 22. So what happened to these samples? If we look at the gamma dose rates, we can see that the gamma dose rates measured for these 2 samples appear to be quite different from the dose rates of the samples directly below and above those. What happens if we, instead of these measurements, take the average between the samples below and above for each of these two samples? Well, the two outliers are no outliers anymore. And so in our view, this confirms that even though it is less less important for USL than for TL, we'll still have a problem of gamma dose rate determination for this site. And so we decided to exclude these two samples for Bayesian modeling of the stratigraphy in what Now, in what follows, we actually did perform modeling using radiocarbon ages for the top of the sequence, single grain OSL, the stratigraphy, and in particular stratigraphic constraints, and we also modeled the systematic uncertainties. Now, to this end, we used a modeling tool which is called Bayesian, and it's specifically designed for OSL dating. And we've shown in the literature already that we gain in precision by using Bayesian, but we also gain in accuracy and also in range, which are about the three goals that any statistical tool should aim for. But beyond that, we may also include in Bayesian chronologies, in Bayesian models, radiocarbon ages that we can calibrate in the software. We also take calibration uncertainties into account, and that's quite interesting because calibration uncertainties correspond to systematic errors, meaning that if one sample has an age which is overestimated, then it is likely that all other samples are overestimated. And here the comparison or the modeling with radiocarbon, that is independent ages, becomes very interesting. And finally, we can impose stratigraphic constraints. So in a word, or in a sentence, ages are modeled all together. So we model the age covariations. Right, so as an illustration of the effect of stratigraphic constraints, here you can see each point corresponds to an outcome of the Monte Carlo Markov chains of Bayesian. And so it is a realization of a pair of ages here for the two samples at the bottom of the sequence. So sample number 11 and sample number 12. We have a stratigraphic constraint imposed between these two samples. And you can see here in the top left-hand corner of this diagram that there is a forbidden zone which translates visually the fact that sample 12 must be older than sample 11, just because it is below in the. Now here is the effect of calibration uncertainties for two samples which come from the same layer, so sample 10 and 11, which come from from stratigraphic unit 22, and you can see here that there is a positive correlation between the ages. In other words, if the age of sample 10 is overestimated, so is in the high range here, so towards the right side of this image, then in all likelihood, so is the age of sample 11. And so this is what I mean by modeling the covariations in. Now, taking all that into account, here is the new chronology that we propose for Jonzac. So you have in red the raw data that I showed you before. You still can see the average and the individual TL ages. And in grid, I plotted the 68% confidence interval for the sediment ages, for the OSL ages at Jonzac. So there are a few striking observations here. First, we get a better precision with Bayesian. Individual age uncertainties amount to 3.6% compared to the OSL ages obtained with the average dose model, which were of 6.3% on average, and to the uncertainties obtained with TL, which amounted to 15%. The second conclusion we can derive from this, from this modeling, is that the Quina period at Jonzac lasted at least 10,000 years and up to 19,000 years, which correspond to the duration highest posterior density interval at 95% confidence. And we can conclude that Quina Mousterian in Jonzac started during marine isotope stage 4 and ended in marine isotope stage 3. When it comes to the outlook, well, we would like to go back to the site for more extensive sampling for the future excavations that should start next year. And we are looking to enlarge the scale of analysis to the ERC program Quina World that will start next January. Thank you for watching.